Okay, I am very happy to be able to introduce Dr. Leon Ofman. He is a scientist at Goddard, NASA, Goddard Space Flight Center at Catholic University. He's also spends a whole bunch of time at Tel Aviv University. I think I last saw him on the Dead Sea in Israel about a year ago. And he also, this semester, is working in Boulder, Colorado, as a faculty fellow at the High Altitude Observatory, HIO, in Boulder. And he's going to give you a little background. He got his undergraduate and master's degree at Tel Aviv University and his PhD at the University of Texas. So he's familiar with the Great Plains. And he's going to tell us about the solar wind. It's all yours.
All right, thank you. Thank you for the introduction. I'm going to talk about the heating and the acceleration of the solar wind, and I want to discuss the processes that lead to the formation of the solar wind. As you can see from the title, turbulence, waves, and kinetic instabilities of the plasma. So I hope some of you are familiar with plasma physics. For those of you that have questions, please feel free to ask. Before going into the technical details, I'm going to talk about the background a little bit and about the solar corona. So as you know, or maybe you now know, the sun is surrounded by an envelope of very hot gases at millions of degrees. Can you hear me well?
No, I think we cannot hear you very well.
Is it on?
Is it on?
It is on.
Okay, then you have to.
Hello?
Down.
Okay.
Much closer.
Maybe I'll put it somewhere closer here. All right. Maybe like that. Okay, I will try to speak up anyway. So what you see here in this frame is an animation, a movie made by the Solar Dynamics Observatory that takes pictures of the sun continuously. It is a geostationary solar observatory that is located above New Mexico. It transmits information about the solar corona using 10 different filters continuously at 4 times the resolution of high definition television, and that allows sort of solar physicists follow the activity of the corona. And as you can see, let me just relaunch this movie. This is the global picture in various emission lines. This is a combination of helium-2 shown in red and iron-9 ionized 8 times shown in green. So it shows the kind of activity we can see of prominences and eruptions, and these are cooler lines and hotter lines, various states of ionization of iron. So these gases around the sun, and the photosphere, of course, below it is much cooler, is only at about 6,000 degrees Kelvin. So the corona is heated to very high temperatures. Of course, it is much more tenuous than the atmosphere below it, so it doesn't require that much energy, but still to heat. But still, we need to transfer energy from a cooler source to a hotter source, so that sort of contradicts our intuition about thermodynamics, where energy goes usually from hotter objects to cooler objects and not the other way around. So that means the heating of the corona must be a non-thermal mechanism, which means that we first convert our energy in the photosphere to some mechanical motions or to waves, and then these waves, as they reach the corona, damp their energy or basically dissipate and heat the corona. There could be other processes of reconfiguration of magnetic fields that generate currents in the corona, and then these currents can be dissipated.
How far is the corona from the photosphere?
Well, we are talking about a very short distance of only a few percent of the solar radii when this transition happens from very hot sort of gases of the corona to very cold, relatively speaking, gases in the photosphere. So there is this narrow region is called transition region, and there the temperature gradient is really very large. So we are talking about 3 orders of magnitude, right? So now, how do we heat the corona, or how much do we need to heat the corona in order to get this very hot gases? So this could be estimated, in fact, by looking at the losses in the corona. And as you can see, I hope the table is not obstructing your view, but you can see here the various loss rates from the various regions of the sun. So for example, and the units here are ergs per centimeter square per second. So in the quiet sun, we have loss by thermal conduction, where the and that is about 2^10⁵ ergs per centimeter square per second. In active region, the losses are much higher because the temperatures there are larger and also density is higher. So we have up to 2 orders of magnitude higher conductive losses. In coronal hole, we deal with cooler plasma. It's still 1,000,000 degrees, but it's not as hot as in active regions, and then the losses by conduction are smaller. The other very important energy loss in the sun is radiative loss, where we lose energy by radiation in all directions, basically. And the corona is optically thin. That means that the photons, as they leave our parcel of plasma, interact only very weakly with the surrounding plasma. So they just leave and take the energy with it. They're not reabsorbed as would be in a dense, radiatively coupled matter. So in the quiet sun, again, we have 10⁵ ergs per centimeter square per second. In the active regions, of course, the plasma, again, emits more because it's more dense and is at higher temperatures. In coronal holes, regions of lower density and temperature, the losses are smaller. Then, comparable loss is the solar wind, as you can see from the last line here. And I'm going to be talking about the solar wind in this talk. So this solar wind is basically loses energy through basically kinetic energy of the solar wind. So I'm going to discuss the heating and acceleration of the solar wind, how we produce or how we energize this matter. So now, the solar wind is a constant stream of plasma and magnetic field coming from the sun. And this is, so we know this from, initially the solar wind was predicted theoretically, but we know this very well from measurements. And there's an example of a satellite observation. It's called Ulysses. Now this satellite, the special aspect of the satellite that it went out of the ecliptic plane of the solar system, and it actually orbited the sun in a polar orbit, going over the poles of the sun. So this is important because the solar magnetic field can be very approximately described during solar minimum as a dipole. So in the equatorial region, you have a bunch of closed field lines, and then you have sort of quasi-open field lines in the polar region. They basically connect somewhere into the interplanetary medium. But so here we have some open field in this region, and here we have a closed field region. Now, so the satellite that went over the poles, basically, incidentally, he had to go first out to Jupiter, so that the gravitational assist by Jupiter would change the inclination, so it would have gone through the polar plane of the sun. So it took quite a few years. And then what you see here below is the sunspot number. So that gives our indication of the sunspot cycle. So this is about a dozen of years of data. So then in the first orbit of Ulysses, the sun was at the minimum of its activity. And in the background here you see a measurement by another spacecraft called SOHO that shows the corona as it was seen in extreme ultraviolet. This is the emission from the very hot gases. And the coronagraph image that shows the equatorial streamers. These are regions of sort of closed field that trap the plasma on a large scale. And what you can see here is a polar plot that shows the speed of the solar wind in kilometers per second. So this picture, this 8-like figure, shows that we have here a region of a solar wind that is about 750 kilometers per second at its speed. So it's much faster than the speed here. The average speed here is maybe 300-400 kilometers per second. So we have two types of solar wind. We have this fast wind that is coming from polar regions, and as you can see, it is quite steady, okay? And actually, it also is low density. While in the equatorial regions, we have much slower solar wind, and it's indeed called slow solar wind, and it's also more variable and more dense. So the variability, of course, comes from the structures that we encounter in the polar, in the equatorial region, that comes from the magnetic field of the sun. It's not necessarily a temporal variability. It could be spatial variability. This is very long time scale until this orbit was completed in a few years. And this is rescaled to 1 AU. So the measurements, of course, were not at the same distance. They were as the satellite orbited the polar. Now, during solar maximum, this was second orbit that again took maybe 7 years or so. So you can see that here we have the corona dominated by the fast wind. So during, by the slow wind. So during solar maximum, right, we don't get this clear separation between fast and slow wind. We see some fast streams, and then they are intermixed with this slow wind. So this slow solar wind is coming from these coronal structures called streamers, and there the process, this suggests that we have different sort of physics, different acceleration process. It turns out that it's not only that the speed of these two types of solar wind is different, but also the heavy ion composition of these winds are different. So, because in the sun, solar plasma consists not only from electrons and protons with some helium, but we also have large number of heavy ions, which much smaller abundance, relative abundance. But this relative abundance, as it's measured at 1 AU, is not the same in the fast wind and the slow wind. So we have different sources of the wind and very likely different acceleration processes. So what is seen on the left is a schematic diagram that shows the solar wind as it is seen, the fast wind basically, as it is seen as a function of distance from the sun. So this is the distance in units of solar radii on a log scale. So the Earth's orbit is about 200, to be more accurate, on average 215 solar radii from the sun. And this is Venus here. This is closer to the sun. And as you can see, the solar wind speed is increasing. It is accelerated from just a few kilometers per second in the lower corona. Then it accelerates out, reaching almost asymptotic, almost the final speed at about 10 solar radii, okay? And then it sort of coasts at a constant speed of 800 kilometers per second. So now, this point here that is marked with this line is the Alfvenic point. That means that beyond this point, the solar wind speed is faster than the local Alfvenic speed. Local Alfvenic speed, for those of you who are not working in plasma, is the speed at which waves, Alfvenic waves, propagate in magnetized plasma. So after 10 solar radii, basically it travels faster than the wave speed. So there is no information basically that goes backwards. So all the waves, the wind travels faster than the waves. So then as you can see here, right, there is also this region where the energetic particles are accelerated by solar wind and other disturbances. And previous missions, solar missions that measured the solar wind only went this close to the sun, okay? So all this region here is unexplored, basically. It is only explored through remote sensing, through imaging or through spectra that are taken from satellites. But there were no instruments that actually flew that close to the sun and measured the properties of the plasma of the solar wind. And fortunately, in July 30, if it's on schedule, 2018, we will have a launch of the Solar Probe mission, which sort of I helped to design. I was on the science definition team. And this mission will basically go so close to the sun that was never explored before, up to 9.5 solar radii from the center of the sun. So only 8.5 from the surface. And the way it will be done, basically, after the spacecraft will be launched, it will be going around or very close to Venus. And by gravitational assist from Venus, but it will get closer and closer from the sun. But as you remember, I was talking about the Ulysses spacecraft that did this change in orbit using Jupiter, but Jupiter is much more massive. So you can very quickly change the orbit of a satellite. But Venus is much lighter, so you need quite a few passes. So it will take years, but already in the first pass it will be in a region, because remember, these are previous missions here. So already in the first pass it will be closer than anywhere before to the sun. And then after a few years it will, as schematically marked here, this is 30 solar radii. This is actually a field of view of an instrument that looks at the solar corona. It's called LASCO. And you can see that it will make many passes inside this unexplored region, or directly unexplored region, and provide information in the region where the solar wind is still subalfvenic. Okay? So why it is important to get to the subalfvenic region? Because basically we should see, or we hope to see, evidence for these processes that accelerate the wind as they are still working, not just remnants of these processes as we see here when the solar wind is already coasting. So here we will see the actual acceleration processes as they happen for the first time. That is the hope, and this is the goal of this mission. The other mission that the previous one is, of course, is a NASA mission. There is another mission that will be launched in October 2018 for similar goals. This is a European mission with some NASA participation. Now, from the point of view of orbit, they don't go as close. They only go to 0.28 AU. Still, it is a region that only a few spacecraft went there. Definitely not with this large suite of instruments. So the advantage there is, of course, they don't get as close on one hand, but on the other hand, because of that, they can carry more instruments. There is more, and they can obtain more detail. There is also UV imaging, X-ray imaging, particle analysis, and so on, heavy ion analyzer. So there will be much more data. This is one aspect of this mission. The other sort of great contribution of this near future mission, that it will go up to the 34 degrees above the ecliptic, while the solar probe mission will stay in the ecliptic plane. So basically it will catch some of that fast wind, although the fast wind sometimes does get into the ecliptic plane as well, because the field lines that are emerging from the sun, they diverge and they curve and they can eventually reach the ecliptic plane. And also the dipole is tilted, so it doesn't go directly at 90 degrees. So, however, here the chance of catching the fast wind directly will be improved because it will go up to 34 degrees out of the ecliptic plane. So these two missions are complementary, and in a sense, of course, and the data from both missions will provide us a view of the solar wind, of the acceleration processes of the solar wind and the fast wind as well as the slow wind that is unprecedented. So just in a few years from now, we will know much more about the solar wind. So, having said that, what do we know now? So, we know that the corona is heated. There are, of course, quite a few ideas that discuss the heating of the solar corona to millions of degrees. And I don't have time to go to all the possible processes. But there are two main directions that have been studied most intensively. The first is what's called the AC heating, which means that we have some variations in the field in the form of waves or shocks or maybe turbulent eddies, okay? And they sort of launched from the solar photosphere in some way, reach the corona, and then they dissipate their energy in the tenuous coronal gases heating the corona. The other aspect relates to the twisting and braiding, gradual twisting and braiding of field lines. And that was originally as well proposed by Parker. So in that case, again, one generates currents in these fields, and then these currents dissipate, and it results in reconnection of the fields, changing their geometry, magnetic topology, and so on, and then we have heating of the coronal plasma. And of course, turbulence can occur in both processes. On one hand, when we have waves, eddies, and shocks, that can lead to turbulence, and then reconnection also can lead to instabilities and fluid instabilities that can generate turbulence. But then eventually, you generate this energy into form of currents or turbulence or waves. You need to dissipate it. That means convert it to heat. How do one does that? Of course, if there are a lot of collisions, then it's fairly straightforward. We have viscosity, we have resistivity, like in a laboratory plasma, for example. So it's very easy to convert these motions into heat, into random motions of the particles. But if the collisions are very infrequent, okay, and the resistivity of the plasma is very low, then it becomes a problem from the point of view of understanding this process. So then one must think of kinetic processes, okay, that replace the role of collisions. So you have wave motions that generate particle motions. These particles generate waves as they move through, they are charged particles, they move through fields. So they emit electromagnetic waves, and then these waves again can interact with other particles. So we have wave-particle interactions, and then these dissipation processes can proceed kinetically, not collisionally, but through wave-particle interactions. Okay? So now, when we look at the sun, look at the data, the solar wind, and we look at the magnetic fluctuations, we see this typical picture. When we take, this is from WIND spacecraft, data from WIND spacecraft that is at 1 AU. So this is a typical spectrum of interplanetary magnetic field fluctuations. Okay, so what you see here, this is our power, the energy content. And this is many orders of magnitude, as you can see here. And this is our frequency. So when we look at very low frequencies, yes, we see this f to the minus 1 power law spectrum. This is from measurement, okay? Now, when we look at this intermediate range, we see a steeper spectrum that shows this f to the minus 5/3 power law. Then, at higher frequencies, this is the iron gyro resonant frequency. At higher than gyro resonant frequency, the power law steepens even further. Right? So Now these parallels are suggestive of the physical processes that cause them. So, for example, we know that from turbulence theory developed by a Russian mathematician Kolmogorov, that in fluid turbulence, basically in an inertial range when there is no dissipation and the turbulence is dominant, then we have this f to the minus 5/3. And we see the same parallel here. So this is very suggestive of fluid turbulence. Although we know it's plasma, there are no collisions. But still, this is what we measure. We find, and this is at 1 AU. We only have 5 particles per cubic centimeter on average. So still we have this parallel spectrum. This is of magnetic fluctuations. And the velocity fluctuations sometimes show similar spectrum. Of course, it depends also on the velocity component. If this is the Alfvenic component, which means in the same direction as the magnetic fluctuation. Then we see there is dissipation above this gyro resonant frequency. So now, what we are trying to understand how these parallel come about, what are the processes that cause them. And another clue that we get is when we look at these parallel at different distances from the sun. This is 0.3 AU, 0.7 AU, and 0.9 AU. And we see these breakpoints of the spectrum. Of course, this breakpoint as well, and these breakpoints, they move to lower and lower frequencies. So as our scales become larger, right, then our frequency of the breakpoint is moving to lower frequency. The same, of course, happens to the gyro resonant frequency. So here it is only a few tenths of hertz. And of course, closer to the sun, where the magnetic field is stronger, the gyro resonant frequency would be much higher. So all these breakpoints must move in as we move from the sun towards the Earth. So that tells us about the nature of the turbulence that is happening in the sun. And we have what's called a turbulent cascade. That means the energy starts from the sun, somewhere from the f to the minus 1 spectrum. And this could be driven directly by some magnetic fluctuations and velocity fluctuations in the photosphere and the lower corona of the sun. This has nothing to do with the internal evolution of the solar wind. This could be caused by, there are several theories that predict f to the minus 1 spectrum. For example, the self-organized criticality has this f to the minus 1 spectrum all the time. But we don't know exactly why we have this f to the minus 1. So this is sort of our driving spectrum of fluctuations that is coming from the sun. But then the turbulence develops in the solar wind, and then the frequency where it happens, of course, changes with distance. And then the energy goes from these higher energy, large scale, it cascades down to the turbulence scale. And then in the turbulence, it evolves as turbulence increase or makes the scale smaller and smaller, decreases the scale as it evolves. Then finally, you are no longer in the fluid regime, because when you reach such a small scale where you are on the scale of the iron gyro motions or proton gyro motions, it is no longer a fluid scale. You cannot even, with your wave-particle interactions, treat it as a fluid, because you have to consider the resonances, or the resonances that occur due to the field fluctuation as they resonate with the gyro motion of the ions. So the ions can now absorb directly these waves from the magnetic fluctuation, and then increase their energy in the direction perpendicular to the magnetic field as the gyration radius increases. But of course, still they cannot increase indefinitely, because eventually the plasma will become unstable, and that instability will cause the transfer of energy into the parallel direction of the motion along the field. And so through velocity space diffusion and through the emission of ion cyclotron waves.
So there's a question.
Yes?
Is there any difference between the left hand and right hand polarized waves in terms of where they do?
Right, of course, this is a good point. So because we have the direction of gyration is determined by the charge. So for proton, the resonant frequency will be left-hand polarized. So it will take the left-hand polarized. Now, however, for the electrons, they are right-hand polarized. So, however, their resonance occurs at much higher frequency.
So these lines, they show the other modes, or it's just a fit?
No, this is well. These lines are just a fit, but these lines are measurements.
Yeah, the measurements. Yeah, but the green and the
Yeah, these are
red
fits.
Are just fits.
Yes, these are just fits that show the average slope. Okay, so these are measurements again from another spacecraft called ACE, and you can see again a similar spectrum and steepening for the waves. One other aspect is that you have also you have outward propagating waves from the sun, as shown here. There are these two lines. Okay, so there are outward propagating waves which have more energy, and then about 1 or 2 orders of magnitude lower, they are backward propagating waves. So they are reflected from various structures and they propagate towards the sun. And the interaction between outward and inward can also aid this turbulent cascade process. So just to go briefly over what is shown here. So this is from another instrument called COMP that measures the inner corona, very close to the sun by remote sensing. And there they already see this spectrum. Of course, there are some effects of the oscillations of the sun, the P modes, that affect the spectrum. But it's already in the lower corona. They see evidence of this approximately f to the minus 5/3 spectrum. Now, the other aspect I wanted to emphasize in this figure, this is again measurement of velocity and magnetic fluctuations at various locations from the sun using data from various instruments. So this is log scale. This is distance from the sun. In log scale, as you see, that very close to the surface, you can already see these from spectral line broadening. You can see these fluctuations, and then they increase with distance. And this is seen by a Sumer instrument. This is another spectroscopic instrument called UVCS. This is interplanetary scintillation measurements. I will mention this in a few words. And this is finally what we measure in situ. So this region here is empty, basically. That's where the solar probe will measure. But the other interesting way to measure the waves in the solar wind is using radio astronomy, where you look at distant galactic sources, and then as the solar wind passes between the observer and the extragalactic source, one can see the fluctuations due to the changes, minor changes in the electron densities in the line of sight. And if one correlates it, for example, in two locations, or does an autocorrelation, then one can determine wave properties or the amplitudes of these fluctuations. So this is interplanetary scintillation measurements. So we have this ample evidence of data. This is again. Now I wanted to mention also how do we obtain the spectroscopic data. So for example, if we look at the emission of various ions as noted here, for example, silicon 7 or iron 9 and so on. Now these lines have certain width, and if you have very accurate spectroscopic instrument, you can describe this width very carefully. And the width has two aspects. One is coming from Doppler motions due to the thermal broadening of the ion motions. And then there is an non-thermal component that presumably comes from waves. So because we know the temperature of the plasma very close to the sun by, for example, looking at electron temperature, right? So then we can determine what is the non-thermal part. And that would be attributed to the wave. So what you can see here, this is VNT, non-thermal velocity in kilometers per second. So this is what the theory would predict, this dashed line. And this is the measurement. So close to the sun, you have this very good agreement with theoretical prediction. Now, as you look farther out, this is in solar radii, there is a departure. So the question is, do we have this departure because there's not enough photons, so this is some instrumental effect, or it could be that we have dissipation. These waves dissipate, or they can be refracted. So what we're looking at are different type of waves called kink waves, and they can be affected by refraction. So moving further, so now we have ample evidence of waves. However, this is not all that we know about the plasma. We can, because we can measure in situ the temperatures of the plasma very accurately and the velocity distribution and so on, we can determine, what we find is that there is a relation between the parallel temperature of the ions and the temperature anisotropy. So for those of you who are not familiar with this concept, as we are dealing with normal gases in, or atmosphere and so on, the temperature usually is a scalar. It doesn't have a direction, right? So measure 200 Kelvin or 2 million Kelvin, and this is the temperature. But in plasma, in ionized magnetized plasma, we have a preferential direction of the magnetic field, and the ions can move freely or more freely along the field than across the field. Okay, so there could be a difference between the distribution, the velocity distribution along the field and perpendicular to the field, and this gives us sort of instead of a scalar temperature, now we have a parallel and perpendicular. We have direction for the temperature. So it turns out that if you take this beta parallel, which is the ratio of thermal pressure in the parallel direction to the magnetic pressure, okay, and plot all your measurements as a function of that ratio of the anisotropy, I mean the ratio of the perpendicular and parallel temperatures, you get this typical graph, this diamond-shaped distribution. So this was initially very puzzling, why all these data points fall inside this diamond-shaped structure. And it turns out that if one looks at thresholds of various kinetic instabilities, like the firehouse instability, mirror instability, and ion cyclotron instability, which are determined by these two parameters, these thresholds for, this is linear calculation from solution dispersion relation, shows that there is quite good agreement between the boundaries of these regions and the thresholds for the instability. So this is very sort of strong suggestion. This is from WIND satellite. This is from ACE, and this is WIND, another satellite. So you can see that this effect tells us that the instabilities, these kinetic instabilities, determine the properties of the plasma. So let's say we have a plasma with beta that is set of 1 and isotropy of 10 here, right? What would happen then? Within several tens of gyro periods, or very quickly rather, then the anisotropy would decrease. So at that point would start here in the parameter space. The plasma would very quickly end up here because the instability will develop very rapidly on the kinetic scale on the order of several tens or maybe several hundreds of gyro periods. If we compare this to the ratio of the solar wind expansion, the solar wind expands, typical expansion rate is 10 to the 5. So if we take a parcel of plasma, the velocity of the expansion over a certain distance is 10 to the 5 gyro period. So that means very quickly these instabilities would relax the plasma to this region where it can survive and is below these thresholds. So another point is the velocity distribution. Of course, these instabilities are the result of the fact that the plasma is not Maxwellian. This is a measurement from Helios satellite that went very close to the sun, 2.3 AU, and these are measurements in the slow wind, and this is in the fast wind. So if we look at the slow wind, the plasma becomes Maxwellian very quickly, as then it would show a round shape. But as we look in the fast wind, okay, this is the direction of the field, we see that this distribution is squashed. That means our perpendicular temperature is higher than the parallel. We have velocity anisotropy. Another aspect is, do you see this green or this patch here or here? This shows that we have a beam or this elongated structure. That means we have plasma is not moving at the same speed as a bulk, but we have some particles that have higher velocity, and then particles that are close to the Maxwellian. So that is another source of instability. So we see that we have turbulence in the plasma, direct measurements of turbulence, just to summarize quickly what I said so far. And we have ample evidence for instabilities. We have kinetic instabilities that are indirectly evident from this diamond-shaped distribution, and more directly evident from these measurements. That these clearly are not Maxwellian distribution. If you initiate your calculation with this type of distribution, you will get instability and emission of waves. Okay, let me skip that. So now I'm switching to the second part of my talk, where I'm going to talk about the computational aspects of the solar wind. So the simplest way to, of course, describe the solar wind is by using the MHD equation. The first solution actually was obtained by using one-dimensional equations along the magnetic field. So that was basically fluid equations. But of course, the role of the magnetic field is important, so we solve a set of MHD equations. For those of you who are unfamiliar, so this is our equation of continuity. This is our momentum equation, where we have gradient of pressure, we have gravity, we have Lorentz force, and we have some other forces which I will discuss, the contribution of the waves and the viscosity. And then we have inductance equation and Faraday's law, and then we have the energy equation. Okay? Now, of course, this is the simplest form, where we don't specify what is the heating and cooling process, and we just use a polytropic relation. This is also common in astrophysics. The next step, of course, is we can use thermally conductive equations. That means we consider the effects of thermal conductivity and heating, and then basically our energy equation is modified with these two terms, and we have to consider thermal conduction. And this is, of course, momentum addition due to the wave. This is the next simplification. So using the first type of equation, the polytropic equations, one can get this picture of the solar wind. Okay, this is from Oran et al. 2013. And what you see here, this is the sun here in the circle here. And you can see here, this is the speed of our solar wind at minimum. And this is the Alfvenic surface. So you can see the slow wind here. This is a tilted dipole, and then the fast wind in the red zone. So in order to obtain this picture of the slow and fast wind, and this is, of course, very simple picture, doesn't have all the details that we see, but indeed this is a three-dimensional solution. In this case, the waves are described very approximately. Instead of just including the waves self-consistently, one approximates them with another equation that considers the momentum contribution and the energy contribution of the wave. This is called WKB approximation. So then one can get the fast solar wind. But of course, in measurements we see fluctuations, turbulence, and so on. So one needs to consider the effects of the waves self-consistently. And this is one of the early models that consider the effect of the waves. And as you can see, this is our solar wind without the waves in the green line, showing only smaller acceleration. Then when you add the waves, and depending on the frequency, you get faster and faster wind. This was done quite a while ago. And this is our coronal hole. This is a model of waves that are launched in the coronal hole. And you can see the fast wind as is shown in this red region, and the slow wind is shown. But here the waves are included self-consistently, and the momentum transfer, the energy transfer are described self-consistently. Now, more recently, this was extended. Of course, that model that I showed you in the previous slide started in the corona. So the waves were launched based on the corona. And this is a newer model by Suzuki and Tsuka that started from the photosphere itself. So they had this flux tubes that where they launched the waves, the resolved waves from the photosphere. It's a 1.5D model. And they were able to obtain this fast solar wind with variability that matches what is seen in observations as marked here. So this is the state of the modeling of the wave. But, of course, we know that the solar heliosphere does not consist only of electrons and protons. We also have helium ions. And they carry 20 to 40% of the momentum flux because they are so heavy. So then one needs to, the next level of approximation to consider these ions is to use the multifluid equations. So instead of just having one equation of continuity, we now have basically two. One for protons, one for helium. And of course, if we add more ions, we would need to add additional equations. The electrons, because they are so light, their mass is usually neglected in this approximation. And then one obtains this generalized Ohm's law. And this is the result of this Ohm's law is this electron velocity that depends on the proton and ion velocities and on the currents. And that can be obtained self-consistently. Now, of course, we have, instead of the J cross B Lorentz force, we have this partial contribution from each ion. And this is basically our ion cyclotron frequency in front of this term. So we can describe also the gyration motion of these heavier ions. And the energy equation, again, we have now three energy equations, one for electrons, one for protons, and one for helium, and they all are interacting. So this is sort of the next level of complexity. Now one can use these equations to get the solar wind. This is a three-fluid model that I developed quite a while ago. And the animations show these waves as they propagate outward in a coronal hole, and then the resulting sort of parcels of plasma as they're accelerated radially. This is the darker is slower speed, lighter is a higher speed. And of course the electron temperatures that show the increase due to the deposition of the energy by the wave. So this is a 2.5 three-fluid model. One can also take the results of the model and measure the spectra and see whether it agrees with what we see in observation. Of course, we launch f to the -1 spectrum, but that spectrum steepens very rapidly, and we also see the steepening in the resonance as it is reached. So these are the sort of the average solutions. So one can explore various ions. This is the declaration of protons, helium, oxygen ion. And of course, they are constrained by observations because we know from observations that the ions actually are flowing faster than protons. So they must have additional deposition of energy due to ion cyclotron wave, for example. So now going back to the ion cyclotron waves of heating. So what is heating by ion cyclotron waves? Basically, as we know that the ions are gyrating around the magnetic field, and this gyro frequency is determined by their charge, Z times E, and magnetic field divided by their mass. And then we have this resonance condition as the plasma is moving forward. This is basically Doppler shift. So this resonance means that if the field line oscillates at this frequency, then the ions will absorb this energy very quickly. And of course, as they absorb it, their perpendicular temperature will increase. However, as it increases more than 1, the plasma becomes unstable to the ion cyclotron stability, and then they re-emit the waves which can be obtained from this dispersion relation. This is the typical solution of dispersion relation. So this is for right-hand wave. This is the left-hand polarization, and you can see if, for example, we have more than one species of plasma, we have several branches. So this is our proton. This is alpha branch, which asymptotes at the resonant frequency of alphas, and then this is the proton resonance, which goes up to the resonant frequency of 1. Now if we have flow, then of course it also causes this Doppler shift, these slanted lines. So now, in order to understand this, we need to move to another level of approximation. Yeah, okay. And to do this, it's not possible, of course, to do it with a fluid. So one uses a hybrid model where the ions are described as particles, a collection of million disk model, for example, 17 million particles that are followed as they interact with the field. And then by solving these equations and the expanding solar wind, as schematically shown here, with a driven spectrum of waves, okay, one can obtain the solution. So let me, So what is shown here are the solution of such a hybrid model as that has all protons and alphas, and we'll launch a spectrum of waves inside this plasma in our model, and we see these properties of development of this beam and this elongated structure in the distribution function, very similar to what is found in data. So we can explore the parameters, explore this model parametrically, and in this way we can find what are the parameters that provide distribution functions that are similar to what is seen in observations. So this is, now we're switching from the realm of fluid description, as I showed you in the beginning, the MHD and multifluid, to a kinetic description on the ion scale, and that allows us to study the distribution and the acceleration process of the solar wind. Of course, we can look at the evolution of the distributions, and for example, if we have some drift, as I showed you, between helium and protons, then this drift, of course, is unstable. It generates ion cyclone waves that result in perpendicular heating of protons and helium. But then as we heat this plasma perpendicular, as I mentioned, then above certain threshold, they start to develop their own instability, and then they emit ion cyclone waves, and then this anisotropy relaxes. It reaches saturated state. So that saturated state is determined by the parameters of the plasma, similar to what I showed you from this diamond diagram. So if you take certain parameters of plasma, they can only sustain certain anisotropy, right? So we can recover these processes and these limits in our hybrid modeling approach. So going to the fluctuation spectrum, again, we can look at the fluctuation spectrum in our model, and then we see indeed that when we have this instability, we see this steep spectrum, which is much higher than the Kolmogorov spectrum. Let me just go to this slide here. And then, of course, we also recover this Kolmogorov spectrum at lower frequencies. However, if we reach this, when we reach this cyclotron frequency, we start to see the absorption. This is due to the alphas, and then this is due to protons. So we see, of course, here the waves are continuously driven. So we see that we resupply the energy to at these frequencies. However, we see the absorption effect very clearly. So from Kolmogorov spectrum, we see that we dissipate these waves through the resonant processes, and our slope becomes steeper at those frequencies. So, because we don't have much time, let me quickly go through these turbulent dissipation spectra. These are several examples of dissipation that we see in a model for different parameters. This is for protons on the left side, and this is for the ions, and we recover the break. This is the velocity spectrum. Again, this is our very steep spectrum here in the dissipation range, and more shallow spectrum in the inertial range. So there are the properties in the model can recover what we see qualitatively in the observations. Anyway, so another thing that I wanted to show you briefly is that when we look at the fluctuations in the plasma, they basically, we recover also the dispersion relation that I showed you before, but this dispersion relation now is obtained directly from the fluctuations in the plasma. So we, in the model, this is a model of the plasma, so we recover the actual dispersion relation in the branches. This is the fast multisonic branches, and you can see the evidence for the dissipating branches. So let me skip that part. Too much stuff. And go to summary and conclusions. So basically, just to recap briefly, we see from observation that we have two types of solar wind, the fast wind and the slow wind. And the fast wind has evidence of turbulent magnetic fluctuations. It is highly non-Maxwellian and isotropic and have drifting population of ions. So that is what we see in observations. Then from large-scale MHD waves, we see that the waves can transfer momentum, and this can be recovered with MHD codes, the transfer of momentum from the wave to the solar wind. But this, we still need to understand the small scale and distribution function as well as the heating. And that's where the resonant part of the spectrum comes in. So we have kinetic effects that start from turbulence but end up in the dissipation scale and the gyro frequency scale. And then we have heating with preferential heating of helium ions because they are heated at lower resonant frequencies. Of course, their charge to mass ratio is 0.5 compared to protons, which is 1. And we recover many of the properties that we see in the solar wind in our modeling. So we recover the turbulent spectrum and the steeper spectrum in our kinetic modeling. So the other aspect that we see is the expansion of the solar wind, so that this counters the heating in the perpendicular direction. But we see both in the models and in observation that this expansion does not strongly affect the anisotropy. So still we have strong perpendicular heating, and we can heat the plasma by the resonant processes. The other aspect I didn't have time to talk to is the effects of small scale inhomogeneities on the heating of the plasma that can affect and enhance the heating of the solar wind. So to summarize now, we are by the combination of these global models and the smaller scale kinetic models, we start to understand how the turbulence and the kinetic effects heat and accelerate the solar wind, which is a very important process in the heliosphere. Thank you very much.
So we have now some time for questions or comments.
Okay, what puts the energy into the MHD waves to begin with?
Right, so that's what I was addressing in the beginning of my talk. So we have some photospheric motions that basically provide this f to the minus 1 spectrum of fluctuations on very large scales, on very long temporal scales. So because the sun is constantly changing, and there are fluctuations, for example, due to oscillations of the sun, the P modes of the sun, and then the magnetic fields in the photosphere are buffeted by the motion, the convective motion, and so on.
So that all originates then in the photosphere?
They must originate in the photosphere. Then, of course, as it goes through the transition region, part of these this energy steepens into shocks, and then they interact again with the sort of coronal field, and then eventually you have a wave spectral, which you find evidence, direct evidence from remote sensing in the corona that then drives all these processes.
Do you distinguish any roles of coronal mass ejections or some unsteady processes versus kind of steady flow?
Right. So this talk was about the background state of the heliosphere of the solar wind. Now, on top of that, of course, during solar maximum, we have frequent coronal mass ejections where we basically, these are instabilities, fluid type instabilities in the lower corona, that lift large amounts of mass. It comes in the form of prominence. And then the fields carry this mass as it expands in the heliosphere. It can reach the Earth and cause geomagnetic storms. The wind is the background steady state in which all these fluctuations are propagating. But the wind itself is important because it affects the propagation, it affects our ability to predict space weather, because the propagation of these structures will be affected by the background state of the heliosphere. But that is not the acceleration process of the solar wind.
Let me ask a different type of question.
Sure.
At the beginning, you talked about Solar Probe Plus, which is going to fill in a lot of the missing experimental data. And it's going to 10 solar radii. So the irradiance is 100 times greater than at Earth.
Okay.
How are the instruments even going to survive looking at this stuff?
Well, there is a thermal shield, so the instruments, some of the instruments will be shielded.
Of course, you can't look through the shield.
Right. So that would be some. You cannot look directly in the sun, but you still can look at the plasma that is coming from the sun. So the radiation will be shielded, but the field lines are not radial. So all the material that goes, the solar wind that goes along the field, is not necessarily radial. So you can catch it in your instrument still.
Any additional comment? Otherwise, things like